So far, we have not really worried too much about the size of our memory spaces. We've just worked with words, the 32-bit value stored at every register, and we've not really worried too much about whether we can load every address, whether we can load different sizes of memory or anything like that. In this video though, we're going to have a look at different sizes of memory that we can manipulate using the commands and MIPS. So to start with, we know that every register stores a byte, and so it would make sense that we can access each of these bytes. Now that's what the LBU, load byte unsigned, does. It loads the byte address A into the 8 least significant bits of register R. So for example, were we to load byte unsigned from A into CocoCaf C, or into A0 from CocoCaf C, what we do is we go to CocoCaf C's address and we'd look at the contents, see that that's EA, and we would load EA into A0. Now because A0 expects a 32-bit word, we would have to extend it with zeros, and that's what load byte unsigned does. It uses zeros to extend it to fit the size of the register. And so if we were to do the same with CocoCaf D into A1, then we'd look at CocoCaf D and see that the contents of that address are 1C, and we would load 1C into A1, again extending with zeros. Now you might think that load byte is the right instruction to use, but it expects a signed number and it extends the sign of the number, which is something we'll get onto later, but for now I would stick with load byte unsigned. It will always extend with zeros, so it won't change the value that you're using. Similarly to load word and store word, we can store bytes. So if we were to have this a memory address set up with contents, we could say that we were to use store byte, which stores the 8 least significant bytes of the word in register R to address A. What we could do is we could move bytes around. So if we were to load immediately the value of 4 coffees into A0, and then we were to say store the bytes from A0 into CocoCaf, what that would do is it would look at 4 coffees and say that E5 is the smallest byte, and that's the one that's going to be stored to the address, and it will store E5 at CocoCaf, like so. So let's look at half words. Now we're very familiar with words, they're 32 bits of information, but we can also manipulate half words, which is 16 bits of information, as you might expect. So were we to encounter this situation where we have Boadicea stored at CocoCaf C, we can manipulate the half words that are stored at CocoCaf C and so on. So what does load half word unsigned do? It loads the half word at address A into the 16 least significant bits of register R. Okay, so let's look at how that works. Were we to use A0 and CocoCaf C, what this would do is it would look at CocoCaf C and see that the half word stored there, again using little endian notation, as 1C is stored above it and EA is stored in the actual address. So it would store 1C EA into A0. Again, because we're using the unassigned variant, it would extend with 0. And if we look at another example where we do the same, but with CocoCaf and A1, well, what would it store in A1? It would look at CocoCaf, see that the memory address immediately above it is storing BO, and CocoCaf is storing A0, so it would store BOAD into A1. Again, the load half word instruction treats the 16 bits of information as if it's signed, and it tries to maintain that. So that does a little bit more work, and again we'll get onto that later on. Similarly, we can store our half words if we want. So store half word stores the 16 least significant bits of the word into register R to address A. So if we were to load immediately A0 into 4 coffees, and then we were to say store the 16 least significant bits from A0 into CocoCaf, it would look at A0 and see what's stored there. The 16 bits that are stored there is going to be fees, and it would store that into CocoCaf. So again, all of this using the little endian notation. So let's have a look at some examples. So say that we stored Boadicea into the MyData memory address location, which will be 101 CAF C. So we've loaded that into T0. Then we should have Boadicea in T0. And if we load the half word unsigned from MyData into T1, we'll get 1C EA stored in register T1, again extended with zeros. And if we were to load the byte from MyData into T2, that would just load EA into T2. So far so good. But what we haven't discussed so far is offsets. So if we have the MyData memory location label, we can add 1 to that. So I can load 1 to MyData and that would take me from 101 calf C up to 101 calf D. Or similarly, I could add 2 and that would take me up to 101 calf A, and I could add 3 and that would take me up to calf. So the point of this is, if you have a data label, you can manipulate that by adding on to it, and what we add on to it is what we call an offset. So let's see how this works. If we were to load the byte unsigned from T3 into my data, or from my data plus 1, that would look at the address above 101 calf C, and that would be 101 calf D, and it would load 1C into T3. Similarly with load byte unsigned from T4 or into T4 from my data plus 2, goes 2 addresses above, which is 1001 calf A, and that stores AD, and so it would store AD at T4. And finally with 3, we'd go all the way up to 101 calf, and we would store BO in T5. Again, all of these extend by 0. Now with half words, it's a little bit trickier. We need to have these aligned, but we'll get onto that in the next video. But if we were to say, go to my data plus 2, now this just takes us 2 addresses above, and then we load the half word from there again using little endian. So we go from calf C up to calf A, and we load BOAD into T6. Okay, so let's have a little look at the storing. Then again, we have the same setup, and we load the immediate value of feed C into S0. And what we want to do is store the half word from my data into S0. So what would that do? Well, it would use the my data memory location, which is 1001 calf C, and it would take the 16 least significant bits from S0, which would be DDCC, and store them 101 calf C, like so. And if we were to do the same again, but with an offset of plus 2, that just takes us 2 addresses above. It doesn't change what we're loading from S0, because S0 has remained the same. It's just the data location that we're loading into that's changed. So we would load DDCC into 1001 calf A, like so. Now finally, if we wanted to store the byte from S0 into my data plus 3, we would go into S0 and we'd see that the least significant byte is CC, and we would store CC at 101 calf, because that is my data incremented by 3, and that would give us CC in that location as so. Okay, so let's have a look at a bit more of an in-depth example. So say we have this memory setup, we have the location X, and we have cabbages stored in a T0. So if we load the word from X into T1, well, what would happen? Well, we'd go to X and we'd see that the word at X is body dogs, reading BOD1 DO65, and that would get stored at T1. So T1 gets updated to have the word body dogs, again using little endian to read from the top down to the location we're given. Okay, so if we want to then store the byte from T0 into 101 calf B, then what would we do? Well, we'd look at T0 and see that the least significant bit there is E5, and we would store that at 101 calf B, and that would give us E5 there. So that's how we would do that. That just takes the least significant byte, stores it at the given address. Now let's look at the next instruction. We load the half word unsigned from X plus 2 into T2. So what is T2 going to be? Well, if we know that X is being incremented by 2, we go 2 locations up, and that means we go past calf D to calf A. That's 2 registers above the label X. So what's stored at 1001 calf A? Well, it's BO from the register above, because we're doing the half word, and D1 at the register itself. So T2 should be 0000 BO D1, like so. Again, we extend by 0 just to keep the value the same, and that's what the load half word unsigned does. Okay, so if we store the word from X into T2, what is going to happen? Well, we're going to get BOOD1 is stored there, because we're taking the whole word that is stored at T2 and we're loading that into X, which means that the 3 registers above it have to be manipulated as well, because the word takes up all of those values, and what's stored at X is 0000BOD1. So we load the word in, again using little endian notation so that the register X gets the least significant, and so on and so forth. And then the final instruction is to store the half word from T1 into 1001 calf A. So what is the half word at T1? Well, we know that the half word is going to be D065. So that should get loaded into the register address 1001 Cathay, like so. So that's us. That's everything for this lecture. I hope this all made sense. We'll be doing more of this as we go forward, but if you have any questions about anything we've covered today, please do let me know. Thanks.